All right, we are Vega, Carlson, Tyler, Paul, and Sawyer Smith, and we're going to be talking about wave file oversampling. I'm Vega Carlson, and I'll be starting. To start with, our problem motivation. So, waveforms in music can get very complicated, and modern synthesizers generally use very complex waves. So, to perform some audio effects such as distortion, the sample rate usually needs to be doubled or more to avoid digital aliasing. Doing this oversampling can be pretty computationally expensive, especially in real time. So we wanted to make sure that we could sample audio down and back up and still retain decent quality. And we wanted to test different methods for doing this. So on this, we're going to be using a wave file, a .wav. And these types of files have individual sample points. These are the points that make up the wave in discrete time. As you can see here, labeled original wave. What we're going to be doing is removing samples such that we only keep every nth sample. Here we're keeping 1 out of every 4 samples. Then we'll find an interpolation of the wave. As you can see, the pink line here represents like a linear interpolation. And then we'll be placing the samples back in such that we reach the original sample rate. So because we removed 3 samples above, we're adding 3 samples back in linear interpolation. So to do this, we needed to collect some data, some audio files so that we could work with. For this, we used the oscillator that you saw at the beginning of those slides, that module there. And our input data can be really any wave file, but we wanted to use simpler waves so that we could actually evaluate how they performed visually. We made a waveform which gradually increased in complexity and frequency using that analog synthesizer. And as you can see, we started with this sine wave. Then we went on to more complex like saw waves, getting gradually more complicated waves. They are all still periodic at least, although the frequency can vary. And then you can see the spectrogram view below to get a better idea of our input data. So to start with, we tried a linear spline, which is a piecewise linear interpolation. This is just what was described at the beginning of the slides here. It simply connects 2 points until it can recreate the samples. And as you can see, the linear spline interpolation produced a result that looks very similar to the input waveform. There are some of these big spikes where on the very sharp transitions it wasn't able to be reproduced exactly, but that was to be expected. Otherwise, this is just a difference between the input and output wave, and as you can see, that difference is actually relatively minimal. So let's just go ahead and hear how this performed. We used 8-bit inputs for showing these in the slides, so the audio is not going to be that great to begin with, but here is the 8-bit linear spline interpolation input wave. Here's that wave at 2x resampling. So this is removing every other sample and then placing back in every other sample. And then at 8x resampling, so this is removing 7 out of 8 samples and then trying to add those samples back in. As you can hear, there is quite a bit of distortion involved, despite the fact that it actually looked visually very similar. Here's our code for running the linear spline. You can see here in this for loop down here with the y.append that the linear spline function is exactly as defined. That is the function directly out of the any textbook you would find for numerical analysis. I'll be passing it off the slides to Tyler for talking about the quadratic spline.
Hello, I'm Tyler Paul, and I'll be covering a couple other methods we used for this interpolation. So the second one is quadratic spline interpolation. And so the format was very similar to the linear spline interpolation. We have the same input waveform, and you see with the quadratic spline interpolation, many sharp hills and valleys. Compared to the linear, it's the scale is a little stretched because you see how high it's over or underestimating compared to the linear. And you also see that on the difference, a very large difference. And so next, let's see how those sound.
Here's the input wave. It is the exact same as before. Here's that with every other sample removed and then restored. And then a fair warning before we play this, the quadratic spline at 8x resamplings, this is removing 7 out of 8 samples and adding them back in, is rather loud and kind of alarming. So you may want to turn your volume down before we play this sample. I'll give you a moment to do so. All right, and now I am playing that sample. Maybe. All right.
With that, let's look at the code a little bit. You can see here, as was the case in linear spline interpolation, on the y.append statement near the bottom, you can see that z.append statement. Those are the methods you would find in any numerical analysis textbook in order to create a quadratic spline, and that's exactly what we used here. So now moving on to the final method, the R-cubic spline interpolation. The R-cubic spline is sort of a variation on the regular cubic spline, which uses recurrence relations rather than matrix calculations. So looking at the actual results, we see with the R-cubic spline, there's many weird looking hills and valleys on the interpolation. But it looks pretty good. It looks to follow the input waveform pretty well. And the difference is also pretty comparable to the linear spline overall. And now let's move on to how those sound.
First, here's our input wave, again, same as before. Here's 2x resampling, again, that is every other sample dropped and then restored. And finally, here's 8x resampling, which is dropping 7 out of 8 samples and then trying to restore them via the cubic spline.
So as you listen to those, as you recall, the quadratic on the 8 times did terribly, the linear did not do well, and the cubic spline actually did okay. So that's one big takeaway just from listening to those. Now let's move on to the code. So here it's the same basic structure, and it's just building up those recurrence relations and then plugging them in to get the cubic function, which will be used for the piecewise interpolation. I'll hand it over to Sawyer to talk about some recommendations and our results.
Awesome. So I'm Sawyer, and I'm going to finish out the presentation. What we're looking at here is those graphs that we saw on the slides previously, but they're all lined up with each other now so that we can kind of look at them as a whole, as opposed to just individually. So what we're seeing in that first graph in the top left is the input waves. That's what we're trying to get back to at the end of this whole process. And then in the yellow, we have the linear spline. In the green, we have the quadratic. And in the red, we have the R-cubic. As we can tell, and as we've kind of talked about already, the quadratic did really, really poorly at what it was attempting to do. So we're just kind of going to ignore that for the time being and focus really on the linear and the R-cubic splines. And you can notice, if you look at them next to each other, they actually look really similar in terms of like general shape. It's just that the R-cubic spline has what we're going to call bumpity bumps. It's very bumpy, as opposed to the linear spline, which is surprisingly very linear. And that's relatively true for both resampling by 2x and by 8x. In the 8x, it is a little bit more bumpy when you look at the R-cubic spline, but they do hold that same like general shape. Next slide, please. Thank you. So these are the two difference graphs. Again, at the top, we have the 2x, and the bottom, we have the 8x. Once again, the quadratic didn't work very well, so it's a little bit of a disaster. But if you look at the linear and the R-cubic, which again are in the yellow and the red, they are very, very similar. And actually looking at it, you can notice that the yellow, which is the linear spline, is it's compared to the R-cubic spline, it is more similar to the original input wave. And this was initially something that we based our first conjecture off of, which was that we predicted that the linear spline was going to do the best just based on like the visual representation of it. However, as we heard when we actually listened to these things, it ended up that the R-cubic spline sounded the best. So auditorily speaking, it ended up being the best fit. Next slide, please. Okay, so if we actually look at the linear compared to the R-cubic, once again, the linear is visually, it looks a lot more similar to the input wave. However, as we know, the cubic sounds a lot more similar, whereas the linear had a little bit of distortion going on. And we think that might possibly have something to do with these images over on the right side. As you can see in that linear graph, there's a big kind of grayish line across the middle, and someone can jump in and correct me if I'm wrong, but that means that there's
very little frequency content between the 5 kilohertz and 6 kilohertz range, which may make it sound like there's two individual notes going on instead of a single note. So while at cubic, there is the single note that looks to be right around 800 hertz here and then dips down. That's still true of the linear. We still have this base note, but then because of this discontinuity, it will no longer sound like harmonics and then sound like an individual note that's happening on top of it, and a very high pitch one at that. We can't really confirm that directly, as that's getting into the realm of psychoacoustics, which isn't really our forte, but it's still an interesting result nevertheless.
Exactly. If you want to go to the next slide. So yes, we were very confused by this because, like I said earlier, the linear spline made it look like the linear was going to be a better fit than the cubic spline. However, audibly, we can tell that that's not true. Like it was mentioned earlier, we're pretty sure it has something to do with psychology. So the way that our brains respond to sound, and more or less the theory of like why certain things sound better than others. It's definitely beyond our the scope of what we intended for this project, and I think a little bit outside of our areas of expertise. Next slide, please. Finally, our recommendation with this project, if you want to go for pure like visual aesthetics, then linear spline is probably going to be the way to go. However, that's not super realistic in terms of like the actual application of this project. So if you're looking at it from an application standpoint or a sound-based standpoint, cubic spline interpolation is going to give the best performance in terms of what this code actually tries to do, as it can be heard the best compared to the other two. One thing we can't say for certain is that the quadratic piecewise interpolation does a terrible job of this, and so we absolutely would not recommend using that to do what we were trying to do with this project.